So here we're going to compute the moment of inertia about the YZ plane, which is notated as I sub x. And the solid here is going to be constant density 1. And it's going to be situated inside the sphere of radius 4 and outside the unit sphere. And what we want to do here is compute the moment of inertia about the YZ plane. So this is, as many of these problems are, really more about figuring out the bounds for the region than it is about the calculus itself. The real challenge lies in setting up those limits. And like I usually do, I'll go ahead and sketch out what a cross section of this might look like. This is again going to be the XY plane. And here we've got the vertical axis Z. So we have a sphere of radius 1, which is going to look something like this. And then we'll have another sphere of radius 4. And we can use our imagination that those things are actually round and representing spheres, but something kind of like this represents our volume that we're working with here. And of course we're going to be in this area here as we loop this out. So given that these are both spheres, we should probably use spherical coordinates. Kind of makes sense. The first sphere is going to be rho equals 4. The inner sphere there is going to be rho equals 1. So you'll remember we've got to find bounds for rho, phi, and theta. So here we've already found our bounds for rho going from 1 to 4. Phi is this angle that goes from the z-axis down to some point. So we're going to start up here at 0, and we're going to work our way all the way down here, which is going to be a full angle of pi. So phi is going to go from 0 to pi. And then there's theta. And since we're looping all the way around, making a full circle here, full 360, theta is going to go from 0 to 2 pi. So there's our bounds. And then it's just a matter of applying the formulas. Really, you just have to memorize these formulas. And you set the thing up once you get the region decided. So we'll go ahead and set up our triple integral here. And we're going to go, this is the moment about the YZ plane, or I sub x, which means that the calculation here is going to be y squared plus z squared times our density function. In this case, rho is constant density of 1. And we're doing this in spherical coordinates, so dv is going to be rho squared sine phi d rho d phi d theta. And I can see I forgot my z squared, so let's add that on there. All right, throw on some bounds. We've got rho going from 1 to 4. We've got phi going from 0 to pi, and theta going from 0 to 2 pi. So now we just need to convert our integrand. So we're going to have the integral from 0 to 2 pi, the integral from 0 to pi, the integral from 1 to 4. Y in spherical coordinates is rho sine phi sine theta. So we have a rho squared sine squared phi sine squared theta plus a z squared, and z is cosine phi in spherical coordinates. So I have a rho squared cosine squared phi. And of course we multiply all of that times, and let's be careful here, we got to get parentheses, rho squared sine phi d rho d phi d theta. And maybe just taking one last step here, let's clean this up one more time. Just simplifying our integrand down, as we should always do, as much as possible. That means for us here doing our distribution, so we have rho to the 4th sine cubed phi sine squared theta plus rho to the fourth, cosine squared phi sine theta, d rho, d phi, d theta. Now, if we wanted to find the other moments, I sub y and I sub z, really it doesn't go any different. It's all about the same. The limits are really the key there. Once you have your limits set up, those translate to any of our individual moments of inertia here. So the different calculations will yield different results, but of course the setup will really go about the same.